Hello dear students, this is your chemistry teacher from Bharat Education Society, Kartika High School. We are starting with the second chapter, that is solutions, and this is going to be our second session. Already we had done one session on the introduction, that is the different types of solution. So let's start. The first concept we are going to start today is your vapor pressure. Now what is this vapor pressure? Now if you see here, there is a liquid in the container which is left open, and there is you can see some of the molecules are evaporating. Now same thing if you were to observe in case of a closed container. If you see figure 1, you can see some molecules have started to evaporate. After some time you will see that few of the molecules will start condensing. So a stage will be reached where you will have the rate of evaporation and the rate of condensation almost becoming equal, and this is called as the equilibrium stage. So the pressure that is created because of this vapor is nothing but what is called as vapor pressure. So this is the vapor pressure of the pure liquid. Now let's see what happens in case of a solution where you are mixing two liquids. Now consider a binary solution of two volatile liquids, A and B. So you are mixing A, that is chloroform, and B, acetone. So what will happen? You will have vapors being formed due to A, you will have vapors being formed due to B. Ultimately there will be some condensation and the vapor pressure will be created. But this vapor pressure that is created is not the same as the case of a pure solvent. So this is called as the partial pressure of the component. And to calculate this partial pressure, it is related to the mole fraction in the solution. So it depends on the number of particles that are present in the solution. To understand this better, it was explained by Rawls Law. Now what is Rawls Law? Now it states that the partial vapor pressure of any volatile component of a solution is equal to vapor pressure of the pure component multiplied by its mole fraction in the solution. So simply it is given as the vapor pressure of the solution will be equal to the mole fraction of the particles into the vapor pressure of the pure solvent. Now same thing can be applied for a binary solution. Now suppose that for a binary solution of two volatile liquids, you have A1 and A2. So of course there will be partial pressure due to A and due to A1 and due to A2, which is given as P1 and P2, while X1 and X2 are the mole fractions in the solution. Then according to Rawls law, we can see that the vapor pressure of P1 is X1 and P01, while the vapor pressure of P2 is given as X2 P02, where P01 and P02 are the vapor pressure of the pure liquids. Now according to Dalton's law of partial pressure, the total pressure of the solution is given by the vapor pressure of P1 plus vapor pressure of P2. Now we know that the mole fraction as per the equation x1 plus x2 always comes to 1. So number of moles addition of both the moles comes to 1. So here when you substitute the value of x1 as 1 minus x2, you get the equation as P naught 2 minus P naught 1 into x2 plus P naught 1. This will help us in calculation of the pressure that is built up in the solution. Now for an ideal solution, it can be represented through a graph where you can see vapor pressure against the mole fraction. Here if you consider, you can see that the total pressure that is obtained, that is P1 plus P2, gives you a straight line. Now this indicates that for an ideal solution obeys Rawls law over the entire range of concentration. So there is no deviation, you are getting a straight line in case of an ideal solution. But when you have a non-ideal solution, they do not obey Rawls law over the entire range of concentration. So there you will see a slight change in their vapor pressure. Either the vapor pressure may be more or it can be less. That is, these solutions can show higher vapor pressure or lower vapor pressure than their pure components or expected results. So here we can see there are two deviations that is seen. One is a positive deviation and the other is a negative deviation. Now let's see the positive deviation. So the solutions in which the solute solvent intermolecular attractions are weaker than those between the solute molecules and solvent molecules exhibit positive deviations. Means normally the particles here are highly volatile and they don't remain in the solution. So most of them will start converting into vapors. So the vapor pressure of such solutions are higher than those of the pure components. For example, ethanol and acetone. So here if you see the graph, instead of having a straight line, you can see that there is a slight curve on the higher side. So this is showing a higher vapor pressure as compared to an ideal solution. So it is not obeying your Rawls law. Similarly, when we talk of negative deviation, so the solutions in which the solute solvent intermolecular attractions are stronger, okay, so means here the solute and the solvent actually try to remain in the solution only, they don't leave the solution, so the amount of vapor that will be formed will be much lower over here. So the vapor pressure of such solutions are lower than those of their pure components. Thus you can see that the graph is showing a downward curve as compared to the ideal solution. So here it is showing a negative deviation from Rawls law. For example, phenol and aniline. Now here is a comparison of all the three graphs, where you can see the first one is showing a straight line depicting for a ideal solution. The second one showing you the positive deviation and the third graph showing you the negative deviation. Now the first graph, it is following your Rawls law, while the second and the third graph is not following. Why? Because here in the second one you can see that there is a weak solute solvent interaction and the predicted pressure is higher, okay, because the solute and the solvent don't want to remain in the solution, so they try to remain in the vapor phase. While in case of the third graph, you can see that there is a strong solute solvent interaction and both want to stay into the liquid phase, thus forming less vapors, thus giving you a negative deviation. Now coming to the next, that is your collocated properties of non-electrolytes. Now what is this collocated properties? Now collocated properties are those properties which depend only on the number of solute particles present in the solution and not on the nature of solute particles. So your number of solute particles will determine or affect these properties. Now what are these properties? The first one is your vapor pressure lowering, second is your boiling point elevation, and third, melting point depression and osmotic pressure. In today's session, we will be only discussing about the first property, that is your vapor pressure lowering. Now, what is this lowering of vapor pressure? Now, you already know what is vapor pressure. So, how vapor pressure is lowered? So, as the solute molecules are added to a solution, the solvent becomes less volatile. Now, if you see the diagram below, okay, this first one is showing you a pure solvent where you have some vapors being formed inside the container. In the second one, if you will see here, you will see that some solute is added, but these solute particles are non-volatile. Okay, so they are obstructing the flow of the solvent and from converting to vapors. So here, if you see, the vapor pressure that is created due to the solvent is the vapor pressure created here in the solvent is much lower as compared to the pure solvent. Okay, so this is due to the presence of a non-volatile solute. So the non-volatile solute has lowered your vapor pressure. So as solute molecules are added to a solution, the solvent becomes less volatile, and the solute solvent interactions contribute to this effect. Therefore, the vapor pressure of a solution is lower than that of the pure solvent. Now this can be explained if P01 is the vapor pressure of the pure solvent, okay, and P1 is the vapor pressure of the solvent above the solution. So the P01 is for the first figure and P1 is for the third figure. Okay, so here you can see that P1 will be less as compared to P01. So the change in the lowering of vapor pressure can be given as delta P, which is equal to P01 minus P1. So this equation represents your lowering of vapor pressure. So now let's understand why the vapor pressure of solution containing a non-volatile solute. Okay, this is very important. It is always a non, because this is not going to contribute in the vapor pressure, is lower than that of the pure solvent, because the vapor pressure of liquid depends on the ease with which molecules escape. Okay, you can see here easily the molecules can go into vapor phase. This is for the pure solvent, but here again you can see when you have the solute mixed, the amount of vapors have decreased. So when the non-volatile solute is dissolved in a solvent, some of the surface molecules of solvent are replaced by the non-volatile solute molecules, and these solute molecules do not contribute, okay, very important here, do not contribute to the vapor above the solution. Thus the number of solvent molecules available for vaporization become less. As a result, the solvent molecules at the surface of solutions vaporize at a slower rate than the pure solvent. So this results in the lowering of vapor pressure. Now let's see how Rawls law can be used over here. So Rawls law for solutions of non-volatile solutes. Now what is a non-volatile solute? Here in this case again only the solvent has a vapor pressure while the solute does not contribute to the pressure. So there is vapor pressure lowering. So the law states that the vapor pressure of solvent over solution is equal to vapor pressure of pure solvent multiplied by its mole fraction. So here the contributing factor will be only 1. That is the solution. So for a binary solution containing one solute, we know that x1 is equal to 1 minus x2. Now suppose if it follows that P1, because here only we have one factor contributing, so we are taking P1, the pressure of P1 is equal to P01 x1, which comes to P01 minus P01 is equal to P01 x2. So the equation clearly defines that P01 minus P1 as delta P, that is the lowering of vapor pressure, and hence delta P is equal to P01 x2, and x2 is nothing but your mole fraction of the solute. So the equation shows that delta P depends on x2, that is the number of solute particles. So we can say lowering of vapor pressure is related to the number of solutes. Similarly, relative lowering of vapor pressure. Relative lowering of vapor pressure, it is the ratio of vapor pressure lowering of solvent divided by the vapor pressure of pure solvent. This is also called as relative lowering of vapor pressure. And here again you can see that the first equation delta P is equal to P01 minus P1 is your lowering of vapor pressure divided by vapor pressure of pure solvent. Here again on simplification you can see this is related to x2. Therefore we can say that the relative vapor pressure is also related to number of moles. So it is also a colligative property. Now how can we use this equation? Now we can derive the molar mass of solute using the vapor pressure lowering equation. Now let's see how this can be done. The relative lowering of vapor pressure is equal to mole fraction of solute, that is your x2. Okay, then it follows that x2 delta P, that is lowering of vapor pressure upon pressure of vapor pressure of pure solvent, is equal to x2. Now we had studied last year how to find out mole fraction. Your mole fraction x2 is equal to number of moles of x upon total number of moles of solvent plus solute. So let's see here. When N1 and N2 are the moles of solvent and solute respectively in the solution. Now here we are considering a dilute solution. Okay, so instead of taking N1 plus N2, we will ignore N2 in the solution. Okay, so here your equation x2 becomes N2 upon N1. So your delta P upon P01 is equal to N2 upon N1. And what is your number of moles? How it is calculated? It is calculated by weight upon molar mass. So let's see. Suppose that we prepare a solution by dissolving W2 grams of solute in W1 grams of solvent. The moles of solute and solvent in the solution can then be given as your, okay, your N2 is for the moles of solute while N1 is for the moles of solvent. So W is the weight of solute upon its molar mass, while W1 is the weight of solvent upon molar mass of solvent. So if you substitute this in the previous equation, you will get x2 is equal to W2 upon M2 upon W1 upon M1. Simplifying this further, your final equation here becomes, this is your final equation to calculate molar mass, that is lowering of vapor pressure upon, this is your lowering of vapor pressure upon vapor pressure of the pure solvent is equal to your W2 upon M1 and W2 M1 upon M2 W1. So please remember this formula properly because we will be requiring this for the numericals later on. Okay, let's move further now. Now same formula just now I told you. Let's see a numerical based on this. A solution is prepared by dissolving 394 grams of a non-volatile solute. Please remember, it is very important to check it is non-volatile. Okay, solute in 622 grams of water. The vapor pressure of solution is found to be 30.74 mmHg at 30 degrees centigrade. If vapor pressure of water at 30 degrees centigrade is 31.8 mmg, what is the molar mass of solute? So here you have two components. One is a non-volatile solute, generally we will refer to as 2, and the solvent we will take as 1. So for the variables we will be using accordingly. So here if you see the whatever data is given to you. First let's see, a solution is prepared by dissolving 394 grams of, so W2 here, weight of the solute is 394 grams. Weight of the solvent is also given to you, that is 622 grams. Then mass of water, you can just that is can be calculated, the molar mass, sorry, 18 grams per mole. Then similarly here you have the pressure also given to you. So if vapor pressure of water, that is P1 here is for pure solvent it is 31.8, and for the solution it is given as 30.74 mm. So now using the formula that we saw in the previous slide, okay, this is the formula. We have most all the details given here. There is no requirement for any unit conversion, so everything can be just substituted directly, and the value of M2 can be calculated using the formula. Okay, so just the substitution of the values and you can get the value of M2 as 342 grams per mole. Now this, students, you need to write it down and practice it. Now let's take one more numerical based on this. The vapor pressure of pure benzene. Okay, so vapor pressure of pure benzene with a molar mass is given to you 78 grams per mole. At a certain temperature is 640 mmHg. A non-volatile solute of mass 2.315 gram is added to 49 grams of benzene. So mass of both is given to you. That is weight of both non-volatile solute and weight of benzene is given. The vapor pressure of the solution is given. What is the molar mass of the solute? So here your solvent is benzene, okay, and your solute is a non-volatile solute. So again let's first look at the data given to you. So P01, that is the vapor pressure of the pure solvent, that is given to you. Okay, then you have vapor pressure of the solution given to you. Then weight of both the solvent and the solute is given to you. Again the same way, same formula will be applicable over here. You just need to again substitute the values and rearrange your formula so as to calculate your value of M2. It comes to 72.23 grams per mole. Now both these numericals because these are both solved numericals in your textbook, but still I would suggest that you please practice it. So with this we come towards almost the end of lowering of vapor pressure and how to derive or calculate molar mass using the formula for vapor pressure. Okay, so we will be continuing our session further with the remaining 3 collocated properties in the next session. Thank you for watching, and please, I will be submitting questions for you all as assignment to be solved. You can take help of your textbook and you can go through the PPT again or the video again, which will help you in writing down the answers. Thank you.